Hello students, in today's class we will read about cells which are connected in series and parallel. So these cells which are being connected forms battery. Okay, when many cells are combined, it is known as a battery. Okay, in a battery these cells are combined in many orientation, maybe positive to positive, negative to negative, or it may be positive to negative or negative to positive, like this: positive, positive and positive. It can be negative, negative and negative, or it can be positive, negative, positive and so on. Okay, so when these sort of orientations are there, while combining, their total EMF changes. In some cases, the overall EMF combines up, sums up to give a more powerful voltage, and in other case, this EMF decreases to give the lesser voltages. So these cells combination is same as the resistor, and in the same way we are going to find the formula for their combination. So see over here, like resistors, cells can be combined together in an electric circuit. And like resistors, one can, for calculating currents and voltages in a circuit, replace a combination of cell by the equivalent cell. Like this combination of cells can be replaced by the equivalent cell, which helps us in easy and accurate calculation of other circuital factors. Now we will start with the combination. Consider first two cells in series. So here we are starting with a series combination of the cell. Series combination of cells, where one terminal of the two cells is joined together, leaving the other terminal in either cell free. See, this terminal is free and these two terminals are joined. Then this terminal over here is again free. So we are seeing the combination of two cells in which two terminals are bound and the other two are free. Here E1 and E2 is the EMF of the two cells respectively. If we are connecting it to the cell 1 and this is cell 2, for cell 1 EMF is E1 and for cell 2 EMF is E2. Now we have R1 and R2, which is the internal resistance of the two cells. Now V of A, V of B and V of C is the potential at point A, B and C. See over here, point A is this, point B is in between the two cells and point C is the free end of the cell B. Okay, so at these points we have potential VA, VB and VC. Now VA minus VC will give us potential difference between the positive and the negative terminal in this. Okay, along this cell, VA minus VB will give us potential difference along this cell, and along this cell the potential difference will be given by VB minus VC. Okay, and overall if we will see potential across VAC, this whole thing, if we see, the potential will be VAC, which will be VA minus VC, which is given by this circuital diagram. If you see this circuital diagram, try to analyze. I have combined the two cells C1 and C2 in this equivalent cell. Their EMF is became equivalent and their internal resistance also became equivalent. And we have collapsed this B point We have collapsed this B point and we have potential at VA and potential at C as VC. Now the potential across this whole cell is given by VA minus VC, which is equivalent to these two potentials added up like this: VA minus VB plus VB minus VC. Potential of this, potential of this. Now this minus and plus will get cancelled and we will get VA minus VC, which is the potential difference across A and C. So we will see this in the next page. See, potential across VA B equals to VA minus VB, and this VA minus VB will be written as EMF across cell 1 minus I into R1. This will be named as equation 1. Next is potential difference between the point B and point C, which will be giving us VB minus VC, which is equals to E2 minus IR2. This is the EMF across cell 2 minus current into internal resistance of cell 2. This is our equation number 2. Hence potential difference between the terminals of A and C of the combination. This was our combination. Okay, this was point A, point B was collapsed, so this was point C, and we had this equivalent and this also equivalent. So across this we had potential difference VAC. This VAC equals to VA minus VC, which is equals to VA minus VB. For this, VA minus VB plus VB minus VC. From equation number 1 we will find the value of this, and from equation number 2 we will find the value of this. So it will give us epsilon 1 minus IR1 plus epsilon 2 minus IR2. So we will take the similar together. This is I1 epsilon 1 plus epsilon 2, then minus IR1 minus IR2. Taking the I common and minus common, from here we will get epsilon 1 plus epsilon 2 minus I into R1 plus R2. Okay, so this is our equation 3, which gives us the potential difference across the terminal A and terminal C. Now replacing the combination with a single cell between A and C of EMF epsilon equivalent and internal resistance R equivalent. So VAC equals to epsilon equivalent minus IR equivalent. From, if we are equating equation 1 and I'll write equating equation 3 and equation 4, what we are going to get is epsilon equivalent equals to epsilon 1 plus epsilon 2, and similarly R equivalent equals to R1 plus R2. This is what we will get by equating these two equations. So this is what I have wrote here. Moving to the next. If we connect two negative terminals of the electrode or the two negative electrodes together, we will get VBC equals to negative of E2 minus negative of IR square. What this condition is stating, I will draw. If this is the condition, this is point A, point B, point C. In this case, V of AB will be equals to same epsilon 1 minus IR1. But in this case, the whole thing is being reversed. So VBC equals to minus epsilon 2 minus IR2. Here the internal this EMF of our cell will be reversed. Our EMF, electromotive forces, or the potential of that particular cell will be reversed. So in this case, E equivalent will become epsilon 1 minus epsilon 2, whereas R equivalent will remain R1 plus R2. There will not be any change in the internal resistance, but there will be a change in the equivalent resistor. Now, there are few rules for series combination clearly can be extended to any number of cells, and we have to follow these two steps of the rules. The equivalent EMF of series combination of n cells is just the sum of their individual EMFs. Whatever number of EMF are there, we have to keep on adding. There will not be any other signs involved. There will be just normal addition or just normal summation of all the EMFs. Now, equivalent internal resistance of series combination of n cells is just the sum of their internal resistance. Now I will show for the E equivalent for n number of cell. It will be epsilon 1, epsilon 2, epsilon 3, keep going up to epsilon n. Similarly, R equivalent equals to R1 plus R2 plus R3, and it will keep on going up to Rn, n number of cells. When the current leaves each cell from the positive electrode, and secondly, if the combination, the current leaves any cell from the negative electrode, the EMF of the cell enters the expression for E equivalent with a negative sign. What they are saying, these two conditions exist in a same way when the current leaves from the positive electrode. I will explain this. See, when I'm having this combination, this negative electrode is combined with the positive electrode. Again, this negative electrode is combined with this positive electrode. Every cell is in a proper direction. Okay, so in this case, our E equivalent will be, this is E1, E2, E3, E4 and E5. It will be E1 plus E2 plus E3 plus E4 plus E5. Okay, but in case this is the condition, see, positive over here is connected with the positive, but here negative is connected with positive, here negative is connected with negative, and here negative and positive are connected. So in this case, current is flowing in this direction. So it will have a EMF of minus E1. This will have EMF of plus E2. This will also have plus E2, E3. This will have minus E4, and this will have minus E5. For this case, see over here, E equivalent will become minus E1 plus E2, then plus E3 minus E4 minus of E5. So here they will show the changes. This is what our second statement, this statement is trying to explain. But what is the case of R equivalent? In all the situations, in all the condition, R will stay same. Stay same. It will be calculated in a similar fashion. There will not be change of any expression in it. Okay. Now moving to the next case. Consider a parallel combination of cells. I1 and I2 are the currents leaving the positive electrode of the cell, but at point B1, I1 and I2 flow in, whereas the current flows out. Okay, here we are having this kind of condition. Okay, our cells are in parallel. Cells in parallel combination. Now in parallel combination there is a difference of the current from the Kirchhoff's. Like in the next lecture we will study about the Kirchhoff's rule, and according to Kirchhoff's rule at a junction the current is divided. Like this should be the sum of currents coming out or flowing in. So in this case this current I will be divided into I1 and I2 at the junction. Okay, but see in series we have seen the current to stay same. Current in all cells was same in series combination. Okay, but I'll write over here current in parallel combination is not same. Okay, now we will move to the next. See the circuitous diagram. Four cells in parallel combination. Okay, so here the current is flowing from the C to B2. From B it is divided into I1 and I2. Then they are entering from the negative terminal of cell 1 and cell 2 and leaving from the positive terminal of cell 1 and cell 2, coming to B1 and moving to point A. Okay, so we will have over here is a VA minus B1, and then there will be some differences across B1 and B2, then it will be V2 and VC. Okay, there are three places. I will mention it with the blue color. One across this point, another across this point, and the third one across this point. Okay, so here since as much charge flows in as out, we have like at junction B1, wait a minute, I'll just rub and make it clear. How much charge is flowing in is coming out also. Okay, see, since as much charge flows in as out, we have I equals to I1 plus I2. There is no loss or gain of charges. So the current flowing and dividing in the sub branches will be same. Okay, there will not be any differences. Now let potential B1 and B2 be the potentials at B1 and B2 respectively. B1 and B2 respectively. Then considering the first cell, potential difference across its terminal is VB1 minus VB2. This is, we are considering the cell number 1. Hence, V is equivalent to VB1 minus VB2 epsilon 1 minus I1 R1, that is across cell number 1. points B1 and B2 are connected exactly similarly to the cell second also. Hence, considering the second cell, we will have V equivalent to B1 minus V of B2. That is equivalent to E2 minus I2 R2. That is across the cell 2. Now combining the last three equations, I1 equals to I equals to I1 plus I2, we will be combining these two equations. We will get, from here we will get I, from here we will get I2. Okay, I will solve it for you here in blue color. See, I will take this equation. V equals to epsilon 1 minus I1 R1. So it will give us I1 R1 equals to epsilon 1 minus V. Then we have I1 equals to epsilon 1 minus V upon R1. This is the formula for I1 which is being substituted in this equation here. Now similarly I will find the I2 from this equation. V equals to epsilon 2 minus I2 R2. Here it will be I2 R2 equals to epsilon 2 minus V, and I2 will be equals to epsilon 2 minus V upon R2. Okay, and now this particular equation is being entered here in place of I2. Okay, then we have taken out the similar terms. And we get this formula. The total current through the circuit is given by I equals to epsilon 1 upon R1 plus epsilon 2 upon R2 minus V into I upon R1 plus I upon R2. So, what exactly we have done is that we have segregated this one and this one. Then we have segregated this one and this one, like denominator is same. So the numerator with the sign of add and subtract can be segregated. That is what we have done in this case. Okay. Now moving on to the next. Hence potential V is given by this formula. V equals to epsilon 1 R2 plus epsilon 2 R2 divided by R1 plus R2 minus I into R1 R2 upon R1 plus R2. This is the potential across the cell C1 and C2 combined parallelly with each other. Potential across C1 and C2 having EMF E1 and E2 and internal resistance R1 and R2 respectively. Okay. So, for this, the potential is given by epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2 minus the current flowing across the system into internal resistance. If we want to replace the combination by a single cell between V1 and V2, the EMF E equivalent and internal resistance R equivalent, we would have V equals to E equivalent minus I into R equivalent. So from here we will get E equivalent as this term, this first term as E equivalent and this second term as R equivalent. Okay, so the E equivalent will be E1 R2 plus E2 R1 divided by R1 plus R2. Similarly, internal resistance equivalent for the combination of the cell will be given by R1 R2 upon R1 plus R2. In simple way, 1 upon R equivalent equals to 1 upon R1 plus R2, and EMF equivalent divided by R equivalent equals to E1 upon R1 plus E2 upon R2. Over here, when there are n number of cells existing, here we have seen only for two number of cell, only for two number of cell for easy explanation and derivation. But when we got n number of cell, how can we do the combination? In this, R equivalent will be written as 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2. I'll write over here 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3, and it will keep on going 1 upon Rn. Similarly, next we have E equivalent upon R equivalent, which is equals to E1 upon R1 plus E2 upon R2 plus E3 upon R3. Similarly, it will go up to En upon Rn. Okay. So this is our equivalent EMF and internal resistance when we are considering these cells. Hope you have understood the concept of combining of the cells, and combination of cells is also equally important when we see the combination of capacitors and resistors. So that's all for today's class. In the next class, we will read about the Kirchhoff's law. So have a good day. Bye bye.